For these Unit 6 preparation problems, we're going to go through and look at several different ideas having to do with heat. So the first one, we have to remember about endothermic and exothermic or other. And we're trying to figure out, well, are each of these situations something that reminds us that is exothermic or endothermic? So the first one, a delta H reaction is positive. Okay, well, we have to remember when we're talking about delta H's of reactions, then we're talking about the difference from the products minus the reactants. And it's always products minus reactants. And so this will be a large number minus a smaller number, and that's going to be positive. So when you're going uphill, absorbing energy, okay, that's going to be a positive delta H. So this is endo. Okay, a balloon which shrinks when placed in the freezer. Okay, well, if it's shrinking in the freezer, that means it's losing energy to the surroundings, to the freezer itself. So it's losing energy, so that's exo. Combustion. Anytime we're burning something, we're burning it because we want to give off energy, so that's another exo. Energy causes interparticle attractions to weaken. Okay, well, if we're putting energy into the chemical, into the substance, and that's making them jiggle around and weakening the attraction, so it must be absorbing some energy, so that's endo. And then the other way, if those particles in between were getting stronger, it's because they're losing some energy, releasing energy. Okay, here's a Q. Q is heat energy, and it's negative, and negative means it's losing energy, so that is exo, heat energy. Okay, solid is heated. If you're heating a solid, then you're putting energy into that, so that is endo. The forming of the OO bond, OO double bond. Okay, when you form a bond, that always releases energy. Okay, so that's going to be exo. The freezing of water. If you're going to get water to freeze, that means you are going to get it to lose some of its energy. Okay, so that's going to be exothermic. Now that's a little confusing because you can think of it the other way. If I were going to melt some water, then I have to put energy into the water. That would be endothermic. But if I wanted to freeze, then I'd put it into a freezer where it's going to, the surroundings would absorb the energy away from the water. So the water itself is exothermic. The system gains energy from the surroundings. Okay, that is the definition of endo, absorbing energy. The temperature of a metal block is hot. Okay, the fact that it's hot, we don't know. So this is, I'm going to say other. Okay, because we don't really know whether it's gaining heat or losing heat. It's just hot. So that's just the way it is. It's not a change. The temperature of the surroundings increases. Okay, if the surroundings increases, that means the system itself must be losing energy in order to heat up the surroundings. So it must be exo. Okay, giving off energy. The temperature of the system increases. That is kind of ambiguous. Is it increasing, the temperature of the system increasing because it's absorbing energy from the surroundings? Then that would be endo. Is it because the system itself is giving off energy, causing, if you had like a solution, then let's say you had like a little baggie, and you had a stuff here, dissolved in liquid. Well, then if that liquid there is increasing its temperature, it could be because the system, the actual chemicals in there is losing energy. So it's kind of hard to say. I'd say this is a little bit ambiguous. On a test or whatever, I think, you could ask for clarification. Okay, water is vaporized. Okay, if it is vaporized at 100 degrees, then that means we must be putting energy into that liquid water to get it to vaporize. So it would be endothermic. And this last one, here's a picture. So we're starting here, we're ending here. So from here to here, we are going uphill. Okay, and so if we're going uphill, it's because we're putting energy into the system. That's endothermic. Sloppy, but that's still endothermic. Okay, next part here. It says a block of aluminum, okay, that's 0.9 joules per gram degree, and a block of lead at 0.16 joules per gram degree with the same mass are placed in a freezer and release 50 joules of energy. Which block has a higher final temperature? Well, this little variable here, that comes from the equation where we say Q equals mc delta T. Okay, we're going to be seeing that quite a bit. And what this C stands for here is, it's the specific heat constant. But the way to think about it is how much does a substance resist change in temperature? Okay, how much does it resist change in temperature? And what we're saying is that the aluminum is resisting change more than the lead is. So with the same energy, that's being lost here, then the aluminum resists change in temperature better. So it's going to end up, it starts at a high temperature and they're going down, down, down. So since the aluminum resists change better, it's going to end up with the higher final temperature. So the aluminum is going to have a smaller temperature change than will the block of lead. Now in number 3, this is similar, and the idea here we're talking about heat of vaporization, and delta H of vaporization tells you how much a substance resists change in phase. So if we have a liquid, the larger the heat of vaporization, the more it's going to resist changing from a liquid into a gas. So here we have methanol, its number is 35. Here's ethanol, its number is 38. So ethanol is going to resist change in phase more. So it says they're heated, absorbing the same amount of energy, which has a greater number of moles of liquid remaining. Okay, so which one was better at resisting the change? And so that would be ethanol. Now, for both of these problems, you could go through and just do a little mathematical version, just put some numbers in, moles, and just calculate which one is going to have the greater amount of liquid remaining. But you can also just kind of think of it logically. So delta H is change in phase, resist change in phase, and the C, specific heat constant changing, resisting changing temperature. Question 4, this is kind of the more involved question. And this is a standard here where we have a hot object, placed into a cold liquid, and we're supposed to figure out what is the final temperature. So if we want the final temperature, let's just define that. So let's say T equals the final temperature, and we know that the equation for absorbing and removing heat is Q equals mc delta T. So I'm going to have Q equals mc delta T for the zinc, and I'm also going to have Q equals mc delta T for the water. The difference is the zinc is a cool object, no, it's a hot object that is cooling down, and the water is a cooler object that is warming up. And the other part about this is the Q from one case is heat lost, and the Q in the other case is heat gained. So Q in one case equals negative of the Q in the other case. So first off, let's set up our two situations. So for the zinc, we have 30-gram block, and we know that our C is 0.39, and that is joules per gram degree. And what's our temperature? Okay, it's at 100 degrees, and it's going to end up at T, and our definition is always final minus initial, so the change in temperature is going to be T minus 100 degrees. Okay, for my water, then I have M is my mass, since it's a 200-gram sample, and it has a value for Q 4.18 joules per gram degree. And its change in temperature, again, final minus initial, so it's going to be T minus 22. Now, obviously, my final temperature is going to be somewhere between 100 and 22. So when I do T minus 100 for my zinc, that's going to be a negative number. And when I do T minus 100 for, this one, that's going to be a positive number. But that makes sense because when I put these two equations equal to each other, Now one is positive and one is negative, so it's going to be negative of it. So I'm going to go ahead and throw in a negative here. So I'm going to say that this is the energy lost is equal to the negative of the energy gained. And now you can see I just have a big algebra equation to do here. Now let's go ahead and start doing the numbers. Okay, you can see what I did is I just did algebra. I did 30 times 0.39 times t, and now that's a negative, so I said minus 30 times 0.39 times 100. That's my left side of my equation. Then I have my negative 200 times 4.18 times t, and it's minus, so I have minus minus, so it's plus 200 times 4.18 times 22. Okay, now I'm going to start doing my numbers. Okay, I've taken this portion here and said 30.39 times t, I got 11.7 t. Okay, minus, I did 30.39 times 100, I got 1,170. I took this part, okay, minus 200, 4.18 in t, so I got negative 8.36 t. And here, 200 times 4.18 times 22, I got 18,392. Okay, now I'm going to put like terms together. So if I add things to both sides, then I can get rid of my 836. So 11.7t plus 836t equals, I have 18392 plus 1172. Okay, and I'm going to combine those terms. And we can see when I put those together, I get 11.7t plus 836t, which comes out to be 847.7t. I put together 18,392 plus 1172. I got 19,564. To get t by itself, divide both sides by 847.7, sorry, and I end up with 23.0789, which I'm going to round off to 23.1 degrees Celsius. So if I started with water at 22 degrees and zinc at 100 degrees, okay, water resists change so much, and there's a lot of it, that when I'm all done, my final temperature here is 23.1 degrees Celsius, 23.1.1. Okay, and that's my final temperature. So just a quick review. I want to do Q equals MC delta T for the block. I want to do Q equals MC delta T for the water. And I'm going to make them equal to each other, except that there has to be a negative in here because one is heat gained and one is heat lost. I make my T the final temperature, and temperatures are always, deltas are always final minus initial, so it's T minus 100 and T minus 22. After that, it just becomes an algebra problem where I try to be very careful because I tend to make mistakes on those and get a final answer of 23.1 degrees Celsius. Phew. Okay, next one. We have a 5-gram sample of ice at negative 15 degrees, and we're going to heat it with 3 kilojoules of energy. And I'm going to change that to 3,000 joules of energy. Okay, 3 significant figures, but I won't worry about that now. And we have some information here. So we want to know what is the final temperature of this sample. Well, we're asked for the final temperature. We're also asked for what state is it in, and to sketch the heating curve for this process. And I would like to do the heating curve first because it'll help me think about my problem. So what's happening is I'm starting down here at negative 15, and at negative 15 I'm going to use some of my energy in order to warm up my liquid. And so that little segment is going to be a Q equals MC delta T problem. And depending on how much energy that takes, I may have to stop here or I may be able to go on. Okay, the next segment here is now I'm going to melt my substance. Okay, and when I melt it, then I'm just using my delta H of fusion. Okay, so the Q here is a delta H of fusion times the number of moles, so that's kilojoules per mole times moles. And then after that, I have another segment where I'm going to be warming this up. Okay, and depending on how much energy I have, it depends on how far I'm going to get with that. So I'm going to do my red segment here, first one, see how much energy I have left, try to do the green part here and see how much energy I have left, if any, and then I'll start doing some more with the yellow part here. And again, this is Q equals mc delta T, but my C is going to be different in this case than it will be here, because heating up ice is going to be different than heating liquid. So with that in mind, let's go back and do the calculations. So we're staying here where it says, okay, first thing we have is Q equals mc delta T, and that's just, we're taking 5 grams of ice, and the 5 grams of ice, for ice, the C, here it is, 2.10, okay, joules per gram degree. And we're going to go from 15 to 0 because that's the freezing point of ice. So there's be a 15-degree change. Okay, so we're going to say 5 grams drop out and degrees drop out. So 5 times 2.10 times 15 is equal to 157.5, and that is joules. So I've just used up 157.5 joules of energy. So at this point I have, I have 2,842.5 joules. Okay, so after melting my ice, I have that much energy. Okay, my next stage will be to try to melt that ice. So see how much energy it's going to take for that one. So for this, Q is equal to, I'm going to use my heat of fusion. So that's kilojoules per mole. So I'm going to take the number of moles times the heat of fusion. So number of moles times the heat of fusion. Okay, but I don't have moles, I have grams, but that's no big deal. So I have 5.0 grams, and this is water. Okay, and I'm going to go from grams to moles, and we all know that's 18.02 grams for 1 mole of ice, or 1 mole of water, H2O. So that gives me gives me moles of water. And then I have 6.01 kilojoules for 1 mole. And I am working in joules, so I'm going to say 1 kilojoule is 1,000 joules. And when I work this all out, I get a value of 1667.6 joules. So it takes me that much energy to melt that ice. So I'm going to remove that from what I have. So minus 1667.6 joules. So now I have 1174.9 joules. Okay, so going into my next section here where I can do Q equals mc delta T to warm up my 5 grams of water, I have 1174.9 joules of energy to do this with. So we're going to do Q equals mc delta T. And this time I know my energy, so I have 1174.9 joules is equal to, I have my 5 grams, and I have C, which now this is for liquid water, so 4.18 joules per gram degree. And this is going to be times delta T. So I want to find out what my change in temperature, but I'm starting from 0. So whatever my change in temperature will be my actual temperature. So solving for this, I just have to do 1174.9 divided by 5 divided by 4.18, and I get a value here. Oh, sorry, that's not quite right. So my delta T is equal to 56.2. That's 56.2 degrees Celsius. Okay, that's my change in temperature, but since I'm starting at 0, this is also my final temperature. So my final temperature, I'll say T sub F is, 0 minus 56. Okay, anyway, it's 56.2 degrees. So what state is it in? I can tell from here. I'm going to make it, in fact, my picture is pretty good. I'm going to make it a little bit higher, about halfway up. So it's going to be liquid. And here's the heating curve for the process. So starting from frozen ice, cold ice, I have to put some energy in to warm the ice up from negative 15 to 0. That's the red part. And then I have to melt that ice using my next equation. And then now that I have liquid water at 5 grams of that, I'm going to warm that up. And I can see I get up from 0 up to 56.2 degrees. And that's that problem. Okay, number 6. Consider the combustion of butane, which reacts according to the following equation. And notice we're given a delta H of reaction. How much energy is released when 4.5 grams of butane is burned? Okay, well, first off, I'm going to need to know something about my butane. I have C4H10. So it's going to be 4 times 12.01 grams. And 10 times 1.008 grams. So that's going to be 48.04 plus 10.08. And altogether that's going to be a 58.12 grams per mole for the butane. So let's go back here. So I have 4.5 grams of butane, and I know that it's 58.12 grams of butane for 1 mole of butane. And from my balanced equation, I can see for every 2 moles of butane, uh, 5.76 kilojoules of energy is released for every mole of reaction that occurs. So how much energy is released? Okay, I can just add this up or multiply this up. And I calculate that as 0.222 or 0.223, so 223 kilojoules of energy. Okay, which I'm working in joules. It would be 223 joules of energy. And since it says energy that's released, I'm going to leave this as a positive number. If it just said what is the energy, I would say negative 0.223 or negative 223 joules. And that's part A. Now the next part's here. What is the enthalpy of formation, okay, of butane? Now energy of formation of butane, I know that I can calculate the energy. I can do delta H of formation and put them together. And for butane, I'm going to rewrite the equation C4H10 plus O2. I'm going to get 4 CO2s, and I'm going to get 5 H2Os. And if I calculate 4 times 2 is 8, 13 halves O2. So the idea here is heats of formation tell me the energy it takes to form these chemicals, So I am going to form these chemicals. So the heat of formation is negative 393.5, and I'm doing it 4 times, so the delta H of the reaction is going to be 4 times the energy released when I form a mole of CO2. And that's kilojoules times 4, so that's kilojoules per mole times 4 moles. Okay, plus I'm going to have 5 moles times the energy for water, and notice this is the value for water as a liquid, because we're going to return these waters to standard state, which would be a liquid. So 5 times negative 286 kilojoules per mole times 5 moles. And then I'm not going to be I'm not going to form my butane. I'm actually tearing apart my butane. So I'm going to say minus the delta H formation of butane. Now that's the number. I don't know that number. That's my X. So my heat of reaction, we just figured out before, was 0.223 kilojoules. No, I'm sorry. That's for 4.5 grams. Okay, for a mole. So here's for 2 moles, I get negative 5.76 kilojoules. So for 1 mole, it would be half of that, which would be 2.88 kilojoules. So let's go back here. So my number here is going to be 2.88 kilojoules, and that's negative because it's energy released, is equal to 4 times negative 393.5 plus 5 times negative 286 minus X. And what I want to do is solve for X. So I have gone through and set up my equation, okay, with the number of the energy released as I form that compound, CO2, and I form H2O, and the negative of this, because I'm not forming C4H10, I'm breaking it up. Then I put in my value, 2.88. So this is just, now this is wrong. Okay, this is 2.88 and 2.88. So let me go back and recalculate my final answer here. 2.88. Now I'm simply putting my like terms together. Okay, so if I want X by itself, okay, I didn't multiply these numbers, get X by itself, so add X to both sides, subtract 2.88 from each side. So 2.88 minus 1574 minus 1430, so I get a value of negative 3001, that's kilojoules. And I would say that that is the enthalpy of formation of butane. Now this is a way we have to do this because, you know, if I were to figure out delta H of formations, okay, I can do that for CO2. I can put carbon and oxygen and measure how much energy is released. I can do that for water. I can put hydrogen and oxygen together and figure out how much energy is released. Okay, notice we don't do this for the oxygen because it's an element, and delta H of formation is the energy it takes to make a substance from its elements, and it's already an element, so there's no energy involved. But the problem here is I cannot put carbon and hydrogen together and it will not turn into butane. So I have to calculate this value for the heat of formation rather than actually measure that. But I can measure CO2 and H2O. So that's how we get the delta H of formation for butane. Okay, 7 is similar. We want to get the delta H of a reaction, but this time we're going to use bond energies rather than heats of formation. And so we're going to take the energy of the bonds that are broken, because bond energy is broken. So I'm going to have 2 of these CO3 ones, so 1072. And I'm going to have 1O2, which is 495. And for over here, I have 1, 2, 3, 4 CO bonds. Okay, but I'm not making these, I'm not breaking these, I'm making these, so I want the opposite of the bond energy, so minus 4 times 799. And I get an answer of negative 557 kilojoules. Okay, and I'm about to run out of time, so really quickly, this says I'm dissolving something and the temperature is going up, and if the temperature is going up, that means this